Okay, let's do some story time about linear regression and where it came from. So I'm going to be reading to you from your textbook a bit, or summarizing anyways, so you can find more details there if this actually interests you further. And if you're even more interested, I can send you some longer detailed papers on some of this history. But I think the history is really important because it sort of grounds where we've come from and where we're going and things like that. Okay, so this all starts back in the 18th century, so in the 1700s, and the main problem that is trying to be solved at the time with some kind of mathematical models or something are astronomical problems. And so in particular, there is an individual called Tobias Meyer, and Tobias collected data on locations from a lot of different places on the moon, and basically he was trying to figure out an equation basically describing the motion of the moon. And so the equation that Tobias came up with was something like this. So that should look kind of familiar from those of you interested in, linear regression in the past, which I'm sure you've all taken at least one course in this where you've covered some of this. And so this should look something like the linear regression model that you're used to. So we've got basically three parameters here: this beta, this alpha, and this gamma. And so essentially he wanted to obtain values for these three unknowns, this beta, alpha, beta, and gamma. And the variables here, this arc and this sine A and G and the cosine A and G, those are basically things that could be observed from a telescope. These angles, sine and cosine, that could be observed from a telescope. And so since there are three unknowns, we only need three distinct observations of the set of three variables to find a unique solution for alpha, beta, and gamma here. But for Meyer, there were actually 27 sets of observations available, and astronomical measurements were naturally subject to some variation, and so there was no solution that actually fit all 27 of these observations. And so his solution was to divide the data up so that the observations within each group were similar in some respect, and then he computed the sum of the variables within each of these groups. And so now there are just three equations in the three unknowns to be solved. So he basically split up the data, the 27, into these three groups, and then he was able to sort of manipulate it such that he could create it so that there really were just three equations and three unknowns. So we computed these values for beta, alpha, and gamma. Beta was 14.5, alpha was negative 1.49, and gamma was 0.134. Okay, so this is in the late 1700s, the 18th century that this happens. So then, in 1805, a mathematician comes along. I'm going to spell this French name because I have looked up different ways to pronounce it, and it comes up a million different ways on the internet. So here's so this is our equation that was derived by Meyer. And we've got an update derived by our French friend. And here's that update. So what's different here? So now this should be starting to look much more familiar compared to what you're used to. One thing that was added is these little eyes here. And so just to indicate that you had 27 of these different observations. We still have beta, alpha, and gamma, But now we have a new term, this epsilon sub I, and that epsilon there was basically the error term. And so the big kind of update here is that we essentially have least squares now, officially published, in which we recognize the equation is not exact, and we introduce an error term. And so when we solve for this equation using the traditional least squares, we end up with 14.5 for beta. We get negative 1.5 for alpha, and we end up with 0.09 for gamma. So pretty close to that original formulation that Mayer came up with. So the least squares solution is a little bit more satisfactory because you don't have to actually arbitrarily divide into groups. You can just solve it as such. And Carl Friedrich Gauss actually claims to have derived this equation prior to this being derived and published, although he didn't actually publish it. And so at any rate, Gauss did publish in 1809 showing that the method of least squares is optimal. And we're going to be talking a lot about that optimality in this class. So for many years, this least squares equation here, this was used in the physical sciences, and the main reason people used this was when they were trying to resolve basically problems of overdetermined linear equations. And so if you remember at the beginning, the problem was that we had these three unknowns. He had 27 data points. Mayer handled this by splitting them into three groups and then basically kind of solving it such that he reduced the dimensionality that way. And then it went on to kind of get this least square solution that we're familiar with. But it wasn't until later that linear equations were suggested empirically from the data rather than from theories of physical sciences. And that's where Francis Galton comes in. And unfortunately, Francis Galton is not a very nice figure in a lot of ways. We have a lot of unfortunate figures in statistics like this. And so Galton has a lot of history with eugenics and bad behavior for sure in that regard. And so Galton was important because he basically helped move statistics into the social sciences and coined the term regression and basically came up with, demonstrated how you could use this method for being able to assess the relationship between empirically observed variables. And so, for example, a famous one is he looked at the height of parents, and he looked how that was related or correlated with the height of children, and was able to plot that data and calculate the actual coefficient or the beta coefficient for that relationship. So that's a little bit about the history, kind of up until now of what has been done in linear model space. Hopefully that gave you a little bit of background into kind of where this all came from and where we're going to go with it. Next, we're going to be talking about the actual linear model, probably as you're used to seeing it with the betas and such, and how to actually estimate those betas appropriately.